So good evening now. We will be starting on our week 12 problem solving section. So in the previous week, what we saw was we started with the we say the field of stochastic hydrology. Basically, in stochastic hydrology, we saw that whatever the variables that we are dealing with in the hydrology and hydraulics. Basically, they all are associated with some randomness. So they can be assumed to be, they can be said to be a random variable. And when we try to predict or when we try to uh, focus such variables, then there will be always it will be associated with some randomness. And like whenever we deal with a data set, like for example, if we take a rainfall data set, so the rainfall data set, we will be collecting the data from the rain gauge station. So how we measure that, we always so. So if we measure the data, we collect it for say for example for 30 years we are having that data. Then we will be doing analysis on these, assuming these 30 years data is the representative of that particular location, right? So in actual, it is not. The rain has been happening in that particular location for so long, right? So within that, we are taking only a smaller period of 30 years and then doing analysis. So such analysis we had already discussed in the previous class. Such analysis is called descriptive statistics, where we try to describe a particular variable. We are trying to describe a particular variable, say for example rainfall, with the available data we are having. For example, 30 years data we are having. We are trying to draw conclusions about that particular location's rainfall using this 30-year data. So we are making conclusion by the mean. That is a measure of tidal tendency. It can be mean, median, or mode, and we are making conclusions based on its variance. We are making that is the variability in that particular location. We are making conclusions whether the it is uniformly distributed like that. So that is what is called a descriptive statistics. We already saw that. And then there is something called an inferential statistics. So inferential statistics are something that we are making assumptions about the population. Population means we don't have the population with us. Population means it is a very data from the very existence, very starting when the rainfall started happening, and in the future also. So we don't have the data, right? So we are assuming we are taking out samples and we are trying to draw conclusions about the population using the sample which we are having. So that is called influential statistics. So in this course, we had focused only on the descriptive statistics, not influential statistics. I think you will be learning in the like higher level courses like stochastic hydrology. Okay, so then we came to something called return period. So return period also we have discussed in detail. Return period is nothing but the recurrence interval. That is a flood if say some amount of rainfall, like some amount of rainfall, X amount of rainfall causes flood, and this amount of rainfall comes after like 10 years. The return period is 10. That is after a gap of 10 years it can come. The probability of occurrence will be 1 by 10, right? So once in 10 years it will come. So in a 10-year period, how much time it can come is 1. So the probability that it will come in a 10-year period will be 0.1, 1 by 10, right? That is something called a return period that also we saw. And we saw connecting to return period something called the exceedance probability. So from that exceedance probability, that is probability that we are fixing a threshold. Say we are saying that in a particular location, if rainfall happens greater than this particular threshold, then it may cause a flood. So we are making assumptions. Or if we are dealing with the what we say, if we are dealing with discharge data, we are making assumption in this particular discharge station. If say in the upstream of Yamuna, there is a gauging station, and we are saying if the discharge is exceed this particular value, then it can cause a flood in the downstream. Okay, so these thresholds we are fixing, and we are seeing the probability that the discharge of the rainfall exceeds this particular value. So that is called the exceedance probability. and it was related to our what we say return period, right? So can start with that concept because we will be mainly focusing on that particular concept only in the final lectures. So that is return period. So return period is associated with an event of an event. It can be flood, it can be drought, it can be hurricanes or any extreme events we can or extreme rainfall events. Return period of an event. So if that is T, okay. So say the probability of some variable, hydrological variable, it can be rainfall, it can be discharge. So that variable exceeds a particular threshold, XT. So XT is the threshold that we are fixing. If the rainfall is above this particular value, so that probability is the exceedance probability, right? So this exceedance probability is given by inverse of T. That is the probability, the recurrence interval is T, right? So once it will occur in T years, the exceedance probability is 1 by T. Understood? So next, in this particular lecture, we'll come back to one new terminology that is called risk. Okay, so something is called what is a risk? So risk is a variable that we extensively use in the field of hydrology. That is, we try to find the in particular, okay, what is the risk of flooding there? What is the risk of drought there? And based on these risk values, so there are many multiple techniques to quantify this risk, this particular terminology called risk. So once mainly we will be in research we will be using probability and statistics for these concepts to define risk, or we will be running some models, and through the model outputs we will be trying to we will be applying these statistics and on to the model outputs and trying to quantify the risk. So once we get the risk, then we can know which all the locations need attention, which are locations that need less attention. And then if we have that picture clear, then we can make the policies or make the structural improvements to focusing on those locations so that the risk there can be minimized. So if we come up with some intervention like reduced pumping or giving subsidy to pumping and subsidized pumping or something like we are constructing an embankment to control flood. So these are policies which we made. And once these are made, we can analyze the same data set which after this embankment has come, then we can see whether the risk has reduced or not. So in the field of hydrology, we use this particular terminology. Okay, so what is risk? So risk is nothing but uh, how much is the chance? So we can say higher the risk, we can say there's a greater the probability of an extreme event that we define. So higher the risk of the location, so it is greater, more vulnerable to that. So that is how we define risk. So if you say higher, if a particular location is having a higher risk, there's greater probability for an extreme event that we have that we define, right? So we can tell the exceedance probability. So the exceedance probability P was x greater than some x threshold xt. We define it as 1 by t, right? So this can be written as a probability of x less than or equal to xt. That is the inverse. That is the probability that x will be less than xt. So this is something like a CDF, like cumulative distribution density function CDF. So that is equal to, we can write f of xt, that is CDF of xt, x equal to xt. That will be nothing but 1 minus 1 by t. So this is the probability. So this is the probability. So this is the probability that the variable, so I'm calling it as variable, it can be rainfall, it can be discharge, anything like that. So variable does not exceed the limiting value. So this is the probability. So this is how exceedance probability, this is how the exceedance probability and our return periods are related. So this was clear from the previous lecture, right? Now what we do is, this is the probability that it won't exceed in T years, right? So if we have n years, not, so this also we have discussed, in n years that the threshold that we fix is not exceeded. So this is given by, you know, the probability was 1 minus 1 by t, that it won't exceed in the t years, right? So if in n such years it won't exceed, then what we need to do is we have to raise to power n. Right. If 2 years this shouldn't exceed, or in 10 years it should raise the same probability, you have to multiply. It is like addition. It shouldn't occur in the first year, so it shouldn't occur in second year, it shouldn't occur, so it is addition, right? So n recurring years it shouldn't occur, then you have to multiply it n times, so it will be raised to it, right? So once we have this, then we define the risk. So the risk is defined as the probability that the threshold is not exceeded in n recurring years. So that will be our, so risk is failure. So risk is failure. So we should say not exceeded, instead of not exceeded should be exceeded. Probability that the threshold is exceeded in n recurring years. So there we can write this as 1 minus whatever we were getting earlier. So this is the expression to calculate risk. The risk can be calculated using this particular formula. This is how our risk is connected with the return period T. So this same derivation or concept has been explained by ma'am also. So the only thing you have to remember, this is how we are getting it. So accidents from the accident probability concept, we are coming up with the definition for risk. Okay. So this is the basic concept. So we will be in the today's lecture, we'll be focusing on two things. One is this risk. So we'll be analyzing the risk for different hydrological structures using the similar concept. So one only thing that you have to remember is how the risk is defined is 1 minus 1 in within bracket 1 minus 1 by t the whole raised to n. So this is, you don't have to by heart. This is how we come up with the risk definition. And also then we will be focusing on two other concepts. So they are, the first one is what is a design storm, and the second concept is a design discharge. So design storm and discharge is nothing but, design storm means if we want to, like we said that some location is having higher risk to a particular extreme event, or a particular higher risk that it gets flooded. So then what we do is we try to build an embankment there so that the water can be controlled and released, right? So when we do that, we have to design an embankment. So when we design an embankment, so there it has to be defined for a particular storm. That we call it as descent storm. So we know rainfall will occur, then it will create a in hydrograph, right? So for what rainfall we need to design the storm, and then for what discharge we need to design this particular uh, discharge. We have to create the particular embankment. So these are calculated using the concept of design storm and design. So it can be constructed for any storms. It can be constructed for like a very high peak flood which has occurred maybe once in 100 years. It can be also constructed for a frequent flood which will occur in once in 5 years. Right. So it is basically there what comes into picture is another thing that is called the economic. So how economic is our design? So if a particular location is getting flooded only once in 100 years, there is no need to construct embankment there with all for that particular very high discharge, right? So you can reduce that there. So there is something we have to go in tally with the economy and with the whatever the we are calculating with based on a return period. Then we have to come up with the final design for the embankments, right? So that also we'll be seeing in this particular lecture. So usually, so I will give a brief intro. So I'm Akhil. I have been my PhD in IIT Delhi. I'm currently in my fourth year of my PhD, and I did my BTech from NIT Calicut and my MTech from IIT Guwahati under the supervision of Professor Srija Pekat. And currently, I'm in Delhi. Uh, so we'll start the sections now. So this is the only concept that will be covered today. So it is the almost the end of our entire module. So with the background of the previous class, it would be easier for because we are dealing with the statistics part more today also. Okay, so we can start with the first question. The first question is, a culvert has an expected life of 10 years. So so we need to design not only embankments. If these, these, the urban areas are getting flooded very quickly, right? Like short duration, high intensity rainfall happens, and flash flooding is happening. So there is a need to make culverts because the water has a natural drainage. When water falls on the earth's surface, it has a natural drainage. When we construct such buildings and all, we are disturbing that natural drainage. So when we disturb the natural drainage, it is our responsibility to create a alternative pathway where the water can flow. So that is how we need to design all these culvert by keeping in that this in our mind. When we are not giving them an alternative path and doing these constructions without taking this into consideration, this is the main reason why we are seeing the urban areas are getting flooded. Because once we disturb their natural flow path, it is very difficult uh, for them to flow. Right? They get flooded. There is no other options. Right? So here we will be seeing a problem of culvert. So the culvert has an expected life of 10 years. If the acceptable risk, so risk concept we already saw, at risk of at least one event exceeding the culvert's capacity during the design period is 10%. So risk is given. That is at least once the culvert's of the culvert's design life, it is exceeded. So the risk is already given to us. What design return period should we use? So what is the design return period they are asking? So we know the risk with us. So they have already given us the risk. They are asking us to find the return period. That is the first part of the question. That is clear. Right? What is then next part is what is the chance that the culvert designed for an event of this return period will not have its capacity exceeded for 50 years. The second part is we already designed the culvert, right? Then they are asking what is the probability that the culvert designed for this does not exceeds capacity for 50 years. So we already have the culvert with us. Now they are asking us whether in the 50 years it will exceed or not. What is the probability of that? In a 50-year period, in the next 50 year, whether the culvert its capacity will be exceeded. We need to state a probability for that. Okay. That is the second part of the question. So it is straightforward with whatever concept you know. We know the formula for this, how we are finding it. So you can write it over here. So this is solution question one. Okay. So risk is given by column it as R bar 1 minus 1 minus 1 by T all raised to N. Right. So the question risk is already given. It is equal to zero point 0.1. Right. The zero point 0.1 is equal to 1 minus 1 by T all raised to N. So N is also, you know, so N is nothing but the design. It is the design life, right? So that once in this design life, it has to exceed. So there, uh, N is 10. So the first question got was the risk at least once the event exceeds a convert during the design life. So design life is 10, right? So N will be 10. So from this, we can solve for T. So if you solve for T, we will be getting the return period as 95 years. So based on the risk, the return period that we need to consider to design the culvert is 95 years. So corresponding to this 95-year return period, we'll be finding a particular discharge. That is not a part of this question, but what we'll be actually doing based on the 95 years that we will find a discharge that will be repeating after once it happens today, after 95 years it will be happening. Right, because our risk was very, we kept the risk to be very small, only 10%. That's why we are getting a T of very high value. Okay, so now we are designing our culvert with a discharge that will occur if it occurs today after 95 years, it will occur. So we already designed this. So now they are asking what is the probability that it will be exceed in the next 50 years. Okay, so if so we can say if T equal to 95 years, the risk of the term is 95 years, that the risk of failure over n equal to 50 years. So earlier, the first part, the statement was what is the risk of failure for the design life? That is 10 years. Now it is 50 years. So that risk will be same formula we can use 1 minus 1 minus 1 by t. T is nothing but 95. And we have to consider a period of 50 years. Right, so this will be giving us 0.41. Okay, so the probability, so this is what the probability that the capacity will not be exceeded during this 50-year period. So this is the probability that it will exceed. So this is the risk, right? So this is the probability that it will exceed. So in the question it was asked, second part was the return period will not have an capacity exceeded. So that is the inverse of this, right? So we can write, so this is the risk or the exceedance probability. So the probability, probability that the capacity will not be exceeded during 50-year period is 1 minus 0.41. So that will be around 0.59. That is 59%. So there is 59% chance that in the next 50 years, this culvert, this return this particular discharge that is exceeding the capacity, design capacity can occur. Okay, that is how we deal with such questions. So basically, this thing is different. So this will be seeing while we are solving questions, and this is the solution for the first question. Okay, so basically, the only thing you have to remember what is risk, and the probability that it won't be exceeded in n recurring years, it will be 1 minus risk. Okay, we can move on to the second question. This is also based on the concept of risk only. But so this now we are dealing with drought. So there is not only flood, there is an opposite, some opposite event that is called drought. This rain, very less rainfall, not rainfall periods. So critical drought of a record has determined from the 30-year hydrological data. So we have a sample of 30 years hydrological data, and we have analyzed the drought. Okay, hydrological data it is considered to have lasted for 3 years. The critical drought of record has determined from 30 years hydrological data that it has lasted for 3 years. Okay, the drought has lasted for 3 years. If the water supply design is based on the drought, so we are designing our data supply based on the extreme condition. So that for normal condition, it will anyway satisfy. For the extreme condition also, it will be satisfied. And with a design life of 50 years. So based on drought, we are designing our water supply and our design life is 50 years. What should be the chance that worse drought will occur during the design period? So during this 50 year, what is the chance that the drought will occur? So this is similar to our previous question, right? The thing is that instead of 12 volt, we are designing the water supply system, and here the extreme event is now. So we can start with the start the given data. So what all are given? So given data is so the record length. So we have recorded data for a period. So the record length is 30 years, right? So 30-year data we have recorded, and critical drought duration during this period. So which we analyzed, drought was lasted over 3 years. So 3 years is the critical drought duration that we analyze using the 30-year data, right? So the return from these two data, we can find the return period. So in 30 years, it can occur 3 years. Drought duration was 3 years, right? So the return period is 30 by 3, right? So that is will be equal to return period T is 30 by 3 is equal to 10 years. So in 30 period which we analyzed, which we had data, it is coming out to be 3 years, right? So average duration of one drought, it will be equal to 30 by 3, that is equal to 10 years. Our return period is 10 years. Using this, we can find the return period as 10 years, right? So the annual probability of drought. So the probability of drought for annually, that is, whether it will occur in the next year or not, that will be a excellent probability, that is 1 by 2. It is 1 by 10, that is equal to 0.1. So this we call it as P, right? So we can call it as this is our P, the excellence probability 1 by T. And another thing that is given is the design life. The design life that we need to consider is 50 years, that is given in the question. So now the question is clear that in the 50 years, this particular drought shouldn't come. So the probability that it will come is risk. That is what is considered, right? In the question that is asked, chance at worst will occur. So we have to directly find risk, not the probability that it won't occur. It should occur. What is the risk we have to find? So risk or R bar is given by 1 minus 1 by t all raised to the recurring interval. or the period under consideration. So 1 minus 0.1, 1 that you already find, and this and like is 50. Now this is the substitution. We will be getting it as 1 minus 0.9 raised to 50. So that will be 1 minus 0.9 raised to 50 is 0.0052. So our rest will be equal to 0.9948. So this is the risk associated that the drought, that particular drought will occur in the design life, that is 50 years. Okay. So based on the sample that we collected, we got a 30-year sample. From that, we saw what is the average drought duration. So from that, we came up with our return period. And for that particular return period, we calculated the risk that it will occur in the design life, that is 50 years or the 10 years, in the, that using this particular formula, and we got it as 0.9948. So what we can see, conclude from this, is that approximately 99.5 percentage chance is there was drought occurs in 50 years. That is our design life of our water supply system. So this is how we conclude. Okay, so we can move on to the third question that is also related to the second question. Okay, so it is also connected with the second question. So in question two, what is the chance that most drought will occur during the first 10 years of the design life? So the design life was 50 years. We are now finding the probability that in the first 10 years, what is the probability? And also the first 20 years. First 10 years, what is the probability? And what is the probability first 20 years? This is very straightforward, right? So we know the formula. This is given by 1 minus 1 by t whole raised to n. And we know for this particular case, 1 minus 0.9 whole raised to n. The only thing is the first part n is equal to 10 years and the second part n is equal to 20 years. That's everything we have already tackled in this particular lesson. So then the A part, for the first A part, or we can call it as first probability of the risk for it will occur in the first 10 years. That will be R is equal to 1 minus 0.9 raised to 10. So that it will be coming around 1 minus 0.3487, that is equal to 0.6513. So here the chance that the worst drought will occur in the first 10 years of the design life is 65. So this we can say it as 65.1% chance is there that the drought will come, this extreme drought will come in the first 10 years. And in the second case is first 20 years period drought will come. So here we can directly use the formula risk is equal to 1 minus 0.9 whole raised to n, that is 1 minus 0.9 whole raised to 20. This will be 1 minus 0.1216, that is equal to 0.8784. The probability that it will happen in the first 20 years, it is approximately 87.84 percentage. Right. So we can now have a compare our results, like the probability that chance that the what we say our extreme drought will come in our design life, that is 50 years, that is 99.5%. So at least 99.5% chance is there. right? So almost it will come. It is sure that it will come in the December once. Uh, for first 10 years, it will come. The probability is bit more less, 65.1%. And the first 20 years, it will come. It is also almost very high, like 87.84%. So based on this, similarly, we can find the risk. And uh, this is how we calculate risk if we have the return period with us and also the expected number of years. Hello. Yeah. So here we are already using one formula, that is risk is equal to 1 by t whole raised to n. So if you don't want to by heart this, this is how we are getting it. That also I have shown. That is the exceedance probability is nothing but it is 1 by t. So 1 minus 1 by t is it won't get exceeded. And the probability that it won't exceed in the next 10, n years, it is 1 minus 1 by t whole raised to n. Inverse of that is 1 minus of that is risk. This is how we can understand this particular thing that which I have shared here. From this, you can understand the formula. So it's the same formula only we are using in the every question. Exam point of view, like we TAs are not the ones who are setting paper, and we are part of like not from the ones writing audio which are behind which who will be setting the paper. So we are here only to guide you through the, if you have any doubt, guide you through the your doubts and also guide you through the assignments if you are having any doubt like that. So the paper will be set by IIT Guwahati, I think. So IIT Guwahati and NPTEL. So we have no involvement in that. So of course, like similar questions, ma'am, which have solved in the class and also which is coming in the assignment. So that would be the pattern most probably. And these are questions, these questions also ma'am has told in the previous class and also the statistics class. That is the lecture, uh, the previous and the previous to previous week lecture. Both had this particular section. So these risk questions are like, if some questions come from statistics, this is a very crucial uh, area, that is risk. Not if not risk, the this particular exceedance probability concept, there the question can be there. Okay. So we can move on to the next question. Next question is also related to the same this concept only. So only thing you have to remember is this particular formula, and if you don't want to by heart it, you can bifurcate this formula like within whatever it is there within this particular bracket is nothing but the 1 by t is our accident probability, 1 minus 1 by t is it won't occur. We need it won't occur in n years, like 50 years or 20 years or 30 years. Then we have to raise to power n. The inverse of that and 1 minus that. That will be the probability that it will occur. That is risk. Okay. So we can move on to the next question. So what is the chance that the largest flood observed in 50 years of record will be exceeded during 10 years and 20 years? This is also similar question only. Instead of flood, it has now become drought. So now if you are seeing this question, it is very clear, right? So they have mentioned largest flood observed in 50 years. That means if it occurs today, the next will be after 50 years. So that is means that is the return period of that flood, right? Either in the question they'll straight away say the return period, a flood with a return period of 50 years. If not, if we say, if they can say in this way also, the largest flood observed in 50 years, that is also means return period only. So don't get confused with that. Either they will mention the return period of a flood with a return period equal to 50 years, or they will mention in this way, flood observed in 50 years. That is nothing but T is equal to return period T is equal to 50 years, right? So if we have T, I already told you what T is, it's equals 1 by T. So that is something that comes inside this bracket, right? 1 by T we can find T will be equal to 1 by T, this 1 by 50, that is equal to 0.02. Okay, so now we have two parts. This very simple. Next, it won't occur, it will occur in, it will or it won't occur. That you have to be careful. If you do all this formula and finally come up with the wrong option, then the option can be what is the risk or what it won't occur. What is the one minus risk? So we have to be clear, we have to read the question clearly, whether they have asked about find the risk or find the probability that it won't exceed in that particular 50 years or 10 years or 20 years. So that because both the questions will, both the answers, the risk and one minus risk, both will be there in our options. So it will be intentionally put to confuse you. Right. So you have to be clear, right, whether we need to find a risk or we need to find one minus risk. That it won't occur. Probably it won't occur. Okay. So in this question, you can just glance through 50-year period will be exceeded. Will be exceeded. If something is there, will be exceeded, will not be exceeded. It is here, it is mentioned will be exceeded. So they are talking about risk. Will be exceeded means risk, will not be exceeded, that it won't occur, that is 1 minus risk. So we have to find risk here. Okay. So next 10 years, that is our first part. The next 10 years it won't occur. That probability will be, so, so that probability risk is 1 minus, so the same formula, if you want, you can write the entire thing 1 minus 1 by t all raised to n. So this is our formula, right? So we can simplify it. 1 minus 1 by t is 0.02, that we already have 1 minus 0.02 all raised to n. That is nothing but 1 minus 0.98 all raised to n. Okay, so the risk will be put next. Here the next 10 years there are, so we have to substitute and it has 10 years. Okay, so this 10, so 1 minus 0.98 all raised to 10, that will be 1 minus 1 all which 10 is coming out to be 0.817. Okay, so this will be equal to 0.183, or we can say it as 18.3%. So there is 18.3% chance that this particular flood of 50-year return period will occur in the next 10 years. Okay, similarly, we can move on to the second part, B part. Uh, that is next 20 years. So here we can directly put, we have already simplified the formula. Risk is 1 minus 0.98 all raised to n, right, for this particular case. Same question we are dealing with. So only n is changing here. So it will be 1 minus 0.98 all raised to 20. So that will be coming around 1 minus 0.667, that is equal to 0.333, or we can say 33.3% chance. So the chance has increased. So the first 10 year that flood will come, 50-year return period flood will come in the next 10 years is 18%. The next 20 years the flood will come is 33.3%. Right. Similarly, for if we increase like for next 50 year it will come, then this we have to change and it will okay. So with this concept, you have to only remember two things. We need two things. That is one is return period T. So return period, you know how we can calculate return period. So we'll either do directly given the question or we have to do some thing like this, 30 years, three droughts, the 30 by 3, something like that, we have to be getting a return period. Then once we have the return period, next we need N. So N is nothing but how the years we are considering, whether they are asking us to find for the first 10 years or the 20 years or for the design life. So whatever the design life that we have to do. Only if you remember that, we can directly solve this. Okay. So we'll move on to question 5. If a structure has a design life of 15 years, so design life of a structure uh, is 15 years, calculate the required return period. So we are asking us to find the design return period. So they are asking the inverse problem now. They are asking us to find the return period. It's an acceptable risk. They are giving us the risk and asking us to find the return period corresponding to that. Okay, so it's an inverse problem. Find for a risk of failure of 20%. And the next part is the n values for in a year and over a design life period. Okay, so this two, I think once this obviously one couple more questions are there on risk. When you solve everything, it will be very clear to you the concept of risk. Okay, so here, so we have only one formula. Risk is given by one minus. So if you want, you can write in this way. 1 by t is exceedance probability. 1 minus exceedance 1 by t is it won't exceed. It won't exceed in n years raised to n. Risk it is exceed, so 1 minus this. So this is how we come up with this formula. Okay. So we have our risk formula with us. You don't have to by heart it, you can write it in this way. And in that, the design life is given 15 years. So T is not given to us. T we have to find. And first case is uh, the case of risk of failure. So risk is given. The first case as 20% in any year. Okay, in any year. So that means n is equal to 1, right? So in 10 years or 20 years, if they say it will be n equal to 10 equal to 20. So they are saying n is equal to 1 year. So here, if you substitute n equal to 1, it will simplify as 1 minus 1 plus 1 by t, right? N is 1. If you open the bracket, it will be becoming like this. So that particular risk is given by 1 by t. So that is very clear to you. That is nothing but an exceedance probability. It won't exceed in any year is given by 1 by t. It will exceed, it won't exceed in n years, we have to use the risk formula. It won't exceed in n years is 1 minus 1 by t whole raised to n. It will exceed in n years is 1 minus 1 by t whole raised to n. Understood? So I can remember like this. It won't exceed in any year. That is 1 by t. Not 1 minus 1 by t. 1 by t is it will exceed in any year. 1 minus 1 by t. It won't exceed in n year is 1 minus 1. This is nothing new. This I am just making you more clarity about this particular formula that you don't need to remember. Whole raised to n. Only that whole raised to n. Here, in any year, it will be whole raised to 1. Okay. So risk is it will exceed in n years. That is risk. So whatever we are getting here, 1 minus that. 1 minus 1 minus 1 by t whole raised to n. This is how we come up with the risk formula. Hope now it is very clear. So here the risk they are only given to us. It is 0.2, 20% equal to 1 by t. So from this we can find t, that is inverse of 0.2, that is 5 years. Okay. So we got our return period also with us. Now we have the return period with us. Now we can go to the second part of the question. The second part they have asked risk is, the second part of the question they are asking risk is same 20% and over the design life. Design life is 15 years. So risk is equal to 20% over 15 years. That is design life. Right. So here risk is same, 0.2. So the formula is 1 minus 1 by t whole raised to n. N is nothing but 15. It should occur in 50 years. Right. That risk is 0.2. So this we are just have to simplify this. So 1 by t I'm calling it as p. So 1 minus t whole raised to n, that is 15 is equal to 0.2. So 1 minus p will be 0.2 whole raised to 1 by 15. So if you solve this, it will be coming around 0. Uh, so it will be, no, no, I made a mistake here. So 1 minus p is equal to 0. It is 6.8, right? So, okay, so this won't be 0.2, this is 0.8 because 1 we are taking to the other side. It's 0.8. So, we had 1 year, so we are more taking this is the LHS and this is RHS. So, it is zero point 0.8. So, 1 minus P will be 0.8 whole raised to 1 by 50. Okay. So, then this will be P will be 1 minus 0.8 all this 1 by 15 is something around 0.9852. Okay, so it will be around 0.0148. So we want return period, that is what been asked. So return period T is equal to 1 by 0.0148. That will be approximately 67.6 years. Okay, so So this is how, uh, so now here what we wanted to do was we need to design a structure. Now we are seeing we are keeping the same risk. We are keeping our risk as same for 20%. And we are saying the risk is 20% in any year. Then our return period that we needed to consider was coming out to be 5 years. Now, the second part we said risk is 20% and the risk period, that period we consider is 15 years. So 15 years is there. Then we saw it shouldn't occur in 15 years. So then the return period will be higher. So the design storm or design rainfall or something that we have to consider will be also higher because the return period has increased. If the return period increase, storm will be also having a higher magnitude. Like if it will come only in once in 67 years, then the magnitude of that particular storm or distress will be also higher. Right. Okay. So in this way, we can understand. Uh, Now we can move on to the next question. So this is also, I think, related to the risk. This is the final question related to the risk. Huh. Yeah, this is the last one. Okay, we will do one thing like uh, I have prepared the question for 2 hours. So I will complete this section and whatever the doubt you are having, you can send me a mail. So through the mail, I will be replying or if you want to have a separate call, we can have for that. Okay. Okay. So we have separate, like we can put a meet call uh, with your convenience and my convenience, you will see, and then we can put a call and in that also you can explain. Anyway, you can send the doubt to me through mail, then we can discuss. As a separate session. So the six, no, no, these all are taken from standard textbooks. what all the references textbook man. Ah, those questions which man has suggested in the reference list, from that we have taken. Those are similar questions you created. Hmm. So floodplain regulation prevents construction within the 25-year floodplain. So there is a regulation. So in the beginning of the class itself, I told you that we are doing all this to bring in some policies or regulations to control these things. There is some floodplain regulation to prevent this. If it is comes in a floodplain of a 25-year of flood, then we prevent construction there. Like for countries like Australia and all, if we want, if we won't be able to buy a land where it is uh, frequently affected by flood. If we want, and also there is something called flood insurance. So in Australia and all, if we buy a property in a flood prone area, we have to take something which is mandatory, like a flood insurance is mandatory for us. Right. So similar to that, there is a flood regulation that prevents construction within a 25-year floodplain. What is the risk that structure built just on the edge of this floodplain will be flooded in the next 10 years? This is the question seems a bit practical question, but the concept is the same. So we have the return period because it's said it's a 25-year flood. So we got so the same procedure we'll follow, same technique to tackle similar question. We try to find our T return period. So that is 25-year flood that I mentioned, which is 25 years. Right. So if we have T, we can find 1 by T. That is our accident probability exceeds any year. That is 1 by 25. That is equal to 0.04. Okay. So the first part of the question, what is the risk? They're asking us to find the risk. The structure just built on the edge of the floodplain will be flooded during the next 10 years. So this is already, we have solved many questions today. 1 minus 1 by t all raised to n. So n is here 10 years, right? Next 10 years. So 1 minus 1 by t, we already know 0.04 all raised to 10. So this, if you solve, it will be 1 minus 0.96 all raised to 10, 1 minus 0.6648, that is 0.3352. So risk of having a construction there that it will be flooded in the next 10 years is there's a chance of 33.5%. Okay, so now we can, this is the first part of the question. There is one more part. By how much would the risk be reduced? We have to see the reduction in risk if the construction were limited to the edge for a 100-year return year play. So, uh, so we took our return period as 25. So they're asking us if we took our the return period as 100, and then how much would have been the risk reduced? Okay. So B part, they're asking us same question. Only thing is that our return period has become 100 years. Second question, P is equal to, and second part it is 100 years. So P will be 1 by 100, that equal to 0.01. So now we have to just put that in our this formula. The risk that it won't exceed in the 10 years. So this 10 remains same. The first and second part, the 10 it remains same. So only changes in the return period I have made 1 minus 0.01 whole raised to 10. So this, if you solve 1 minus 0.99 whole raised to 10, 1 minus 0.9044 will be coming around 0.0956. So that will be approximately 9.6 percentage. So earlier the risk was 33.5 when we went with a return period flood of 25 years. Now they are asking, now we increased our return period. For the same flood, we increased our return period to be 100. This flood will comes only once in another 100 years. Then our risk will reduce. Anyway, it will reduce, right? So we need to find how much the risk is reduced. The first case it was 33%. Now it has become 9.6%. So the reduction in risk, so reduction in risk is 0.3352 was the initial risk. Now for 100 years we got the 0.0956, right? So this will be 0.2396 or approximately it will be 24%. So you can see when we increased our return period of the flood we consider the risk of that particular building getting flooded since it is in the floodplain has reduced by 24%. Okay, so we can move on to the next question. So a house of 30-year design life. So 30 years as design life is mainly it will be given the question to take it as n. Okay, so these now we are moving a bit forward, like we understood the concept. We can see how we can solve the question quickly. So if something mentioned like design life, it will be for the terminology n when we are dealing with this concept. Okay, what is the chance it will be flooded during its design life? So it should risk we have to find. Risk for n years. N is equal to 30 years. It is clear to you, right? If the located in the edge of the 25-year floodplain and 100-year floodplain. So it was almost similar what we solved. Right? So uh, instead of 25, it has become 30-year design life. So it is almost like a repetition. So we can solve this question quickly. Whenever we see design life, we have to remember it will be 4 to take the value as n. And they have said the chance that it will be flooded during the design life is located at the edge of a 25-year floodplain. So 25-year floodplain means T is equal to 25. So it means A, the return period is 25 years. Okay. So then our risk associated with that will be 1 minus 1 by 25 all raised to n. What is n? In the first case, it is mentioned that during the design life, right? So n is nothing but 30 years. So 1 minus 1 by this will be 0.96, right? 1 by 25 is 0.04. 1 minus this will be whole raised to 30. 1 minus 0.294 will be equal to 0.706. That is 70.6% chance is there that it will be, risk is there that it will be flooded if we are going with a return period of 25 years and for it design life of 30. And B part, we are just changing our return period. Return period, they are asking us to consider it as 100-year floodplain. So it is 100, right? So risk associated with that. And here also the number of years is for the design life. Okay, 1 minus 1 minus 1 by 100 all raised to n. N is design life only. So it is 30 years. 30, that is 1 minus 0.99, right? All raised to 30. That is 1 minus 0.99 all raised to 30 will be 0.793. So this is 0.261. So that is this. And it will be approximately, we can say 26.1%. So here also you can compare the answers. Initially, when we took the flood return period as 25, the risk was 70% risk was there that it will be flooded. Then when we increase our return period to 100, then the risk has reduced to 26.1%. So almost there is around 30, 40, for nearly 40, approximately 40 or 30, that much Introduction as well. Right. Okay, so that's all about the risk concepts. I hope it is very clear. So we had solved like almost 7 questions related to the risk. Almost 1 hour we are dedicated for that. I hope the concept is entirely clear. So we have the formula 1 minus 1 by 1 raised to n. Using that, 10 is nothing but number of years under consideration. It can be design life, it can be anything that is mentioned in the question. And T is the return period of the flood. It will be mentioned either like flood of this much return period, or it will be like a 25 10-year flood, 25-year flood, or 30-year flood. That is also pointing out to be return period only. Right. So now we move on to the next two concepts. There are two more concepts, that is the design storm and design flood or design discharge. So this is nothing but design storm, as I mentioned in the beginning. In a particular location, when we design a particular dam or a catchment or a culvert or a, not a catchment, an embankment or a culvert, there we need to assume one particular value of value of the peak rainfall or the value of the distribution of rainfall, right? So that on what basis we will be doing. That is where we come to the keys with the what is the intensity of the rainfall that we need to consider for designing that. Okay, so that is you will be dealing in this particular section. Okay, so this is a lengthy question, so more practical oriented question. So you can break down the question into uh, parts, and then first we can try to understand the question, then we can see into the details. A hypothetical drainage basin comprising sub-catchments. So there is a drainage basin or a catchment, we can say. There are sub-catchments or sub-basins are there. Okay. So these all terminologies will be clear to you. There's a drainage basin is there and it has many sub-basins. Okay. Determine the required capacity of storm sewer drainage sub-area for 5-year return period of design storm. So the return period is mentioned 5 years. Right. Determine the required capacity of the storm drain. So we need to come up with the capacity of the storm sewer draining sub-area. So storm sewers, like if you are from in urban area, so there are two. We will see nalas, like we will see drainages to drain wastewater. Along with that, there will be drainages to drain storm water. Storm water is the water that coming from the flood or the storms, right? So, as I mentioned earlier, whenever we are constructing something, we are disturbing the natural drainage path. So, we have to provide them with the alternative paths. That is what called as storm sewers. So, these will be like you can see manholes and all, right? So, these will be connected to this manhole, and then the storm water will be flowing through that. Okay. So we have to design that. So they are basically here the design is we are using pipes, that is circular pipes we are using, and if we want to determine the capacity, we basically want to find the diameter. What is the diameter of that pipe through which the water can flow without causing these issues? Okay. The subcatchment has an area of 4 acres. So we are determine the capacity for a sub area. So we are focusing on one particular subcatchment within that basin. Okay. And the subcatchment's area is mentioned of 4 acres is the area. And the runoff coefficient is also mentioned as 0.16. Okay. So area is given, runoff coefficient is given. And time is inlet time is 10 minutes. So time when the rain starts, how much time it will take to flow to the inlet, right? So that is similar to the time of concentration. That is equal to 10 minutes. Design precipitation intensity. So the design storm intensity, we can directly calculate using this particular empirical equation. So they have made an empirical equation for this particular subbasin and they have directly given the question. So we need not do anything much here. We are given with the intensity. Okay, so we have the design storm with us. We need to find the design discharge. We might need to find the design discharge. So using this formula, if you substitute this T and TD, we'll be getting our design storm, the intensity of that particular storm for which we need to design. So they have done experiments, multiple locations, they would have seen, taken data, and they have developed this empirical equation. You don't have to by heart this, it will be different for any location. Within this subcatchments also, two different subcatchments can have different equations. So this is something we have to see the intensity depends on 2T and TD, where I is the intensity of the so when we are dealing with the empirical equations, you have to be very careful with the units. So whatever units they did the experiment, same units we have to use. Because these constants like 120 raised to 0.175 plus 27, these all are based on the unit units, right? So whatever the experiments they did, whatever the units they use, we have to follow those units only. So the I we will be getting in inches per hour intensity. T is the return period. TD is the duration in minutes. So return period and duration, they are in T is return period and TD is duration period. The ground elevation of inlet and the outlet pipes is the elevation in feet they are given. That is the reduced level of the inlet and outlet of the fluid. So if we have the elevation, we can find the slope of the pipe, right? So this particular question only to make give you a glance that why we are learning all this. So once we solve the entire question, we will be clear why we are trying to find the science term. Now it can be used to find, it can be used to come up with the formula for come up with the computation for the design storm or design discharge or design plan. Okay. So the inlet and outlet elevations are given above mean sea level, and the pipe length is also given. Assume the Manning's coefficient. So these you don't worry. We will be seeing all this in the while we solve the question. This is only to give you a glimpse of what we are actually trying to do in the field. Okay. So don't. So I'll be explaining each and every term. So this is complicated question shouldn't be there in your exams, but this is only just this particular this first question is only give to a glimpse of why we are actually learning on this. Okay, so calculate the flow time in the pipe. So we also need to we need to do two things. The first part we need to design for the capacity. So basically we need to find the diameter of the pipe. That is the first thing. Understood. So we have given with the intensity and all, design intensity and all, we have to come up with the diameter. And also, if we have diameter, then we need to come up with the flow time in the pipe. So the flow rate of the pipe. That's the two things that I've been asking. Okay. So first, I'll give you an overview. Like the equation that we are going to use is called rational formula. This you would have seen in MAM's lecture, rational formula. So that basically gives us the design discharge. The design discharge we can find has Q as given as C into I into A. So this is the formula that you have to just remember. So this formula you have to remember. So the design discharge by a rational formula, it is given by C into I into A. So we can see what are each of the terms. So C is nothing but it is the runoff coefficient. So runoff coefficient we already know it. Runoff coefficient is nothing but runoff by rainfall. It is how much percentage of rainfall is getting converted to runoff. That is given by runoff coefficient. So if we have the rainfall, we multiply with runoff coefficient, we'll be getting the runoff coefficient. So this in this question, they have already given us the runoff coefficient for that particular subbasin, that is 0.6 is given. Okay. I is the design intensity. For what particular intensity of the storm we are designing our drainage system. design intensity. So to find the design intensity, they have already given us the empirical equation. We have just have to do substitutions there. Finally, A is the area of cross section. The area of cross section, once we have the diameter, we can get the area of cross section right. So this is the formula that we'll be using. C, one of version given. I, we can make up the empirical equation they have given to us. And A is the area. So once we can design once we have the basically not the, oh sorry, A is not the area of catch the cross section. It is the area of the catchment. Or the area of the catchment or subcatchment. Here the subcatchment is we are under consideration, right? So area A is the area of the drainage area. How much area we are draining. That is given by A in this formula. I is the design intensity and C is the runoff coefficient. Okay, so it is not the area of cross section, it is the area of the subcatchment. So this is also given, I think. So it is given area is equal to 4 acres. So in this formula, all three are given, right? So only instead of I, all three are given. So I, we have a formula which they have given it as 120 t raised to 0.175 divided by TD plus 27. So here they have also already mentioned T is the return period and TD is the duration. Okay, so T is the return period in years. So T is 5 years. Return period they have already given the question 5 years. This T we are having. TD is nothing but the TD is the duration in minutes. So duration, how much time it will take to the inlet. So that is given by time of concentration. So that is already given the question that is as the inlet time is around 10 minutes. So this is 10 minutes. So we have to substitute in minutes only. Right. So it is just substitution now. 120 into 5 raised to 0.175. T should be in years. Okay, it is return period. And TD is in minutes, 10 plus 27. So when we solve this, whatever we are getting, it will be having a unit of inches per hour. Like it is mentioned, it will be in inches per hour. So if you solve this, it will be coming out to be 4.30 inches per hour. So this is the intensity, this intensity range, that is in an hour 4.3 inches of rainfall. So that is the intensity for which we have to design. So that is called the design storm. Okay, so this is the peak intensity of the rainfall for which we have to design. So that we got, and other two are already given. So this is now the substitution. So the peak design discharge, design discharge Q is given as CIA. So C is nothing but 0.6. I we got it as 4.3 inches per hour, and this we substituted acres, 4 acres. So it will be coming around 10.3 CFS, that is cubic feet per second. So this is the design discharge. Okay, so we got our design discharge with us. Now the next part of the question was we need to come up with the intensity. So we got the design discharge. So till here, it's something that you need to be focusing for your exams because these concepts I have taken in the class. So if we are given with the I equation, design intensity, in the lectures, I have taken many empirical equations, right, to find the design intensity. So through this, we can find the design intensity. Then whatever you need is C and A. C is a runoff coefficient that will be given. A is the drainage area that is also given. So this we need to be understanding because this will can come in the exam. The next part is something that is less important, but once we have this Q, so we found our design storm. We substituted in the rational formula, and we got something now, and that is Q. Now, what we can do with this? How we can do the design? So basically, then what we will be doing is, so there is something called equation called a Manning's equation. So flow in a channel, open channel, we for in open channel we use Manning's equation. So in the hydraulics courses, you will be learning this. So there, discharge is given by one is in this is not is given by 1.49 by n, that is minus 0.2 SF raised to 1 by 2 a raised to a r raised to 2 by p. R is the so A is the area. So we are dealing with a pipe, right? So A is the area of pipe. So pi d square by 4 cross-sectional area, pi d square by 4. And the wetted perimeter R is called the wetted perimeter, and that is given by d by 4. So we can substitute this in this particular equation. Finally, we will come up with an expression for the diameter. You just have to substitute all this. So we will take out d, and diameter will be coming around 2.16 Qn, that is the design storm that we have designed, under root of S naught. S naught is nothing but the Bett's law. This is not here we will be assuming that friction's law and Bett's law are equal. So we can say it as Bett's law only, S naught. Okay. So this is the expression that we are getting for the diameter of the pipe if we have the discharge now. So we first calculated our design intensity. Now we have a design storm. Now we'll put that in this particular equation, Qn, SQn, and find the diameter of the pipe. So that particular diameter pipe we have to design, right? So when we substitute that, then what we'll be doing, the designer will be finding this diameter value. So D is equal to 2.16 into Qn is 10.3 CFS. Okay, by root of S naught. S naught is nothing but the bed slope. The bed slope is S naught we need to find. In the question, the elevations are given, right? 498.43 and 494. So what is the slope of that? So that we can find using the elevation values. S naught will be 498.43 minus 495.55. So this is the elevations divided by the length of the pipe. So length of the pipe is this much. This is nothing but this. The pipe will be laid like this. This particular elevation we know, this particular elevation we know. This difference will give us this particular area divided by the length. So this is given, this will give the length of the pipe. So length of the pipe is 450 feet. 450. And if you solve this, we will be getting the slope as 0.0064. Okay. So just substitute that here 0.0062. Then this whole raised to, so we start one thing. So here it is whole raised to, so when you derive this, so after the class we can try deriving this particular straightforward only. We will be getting the dy is like this, it raised to 3 by 8. Right. So this is also whole raised to 3 by 8. So if you substitute all the values here, you will be uh, so there is one more term q into n is there, right? There is one more term that is q into n that we missed out. That also we need to substitute here. So we dot on the q. So Q into N. N is the Manning's coefficient, right? N is minus man is constant this particular term. Man is coefficient that they have given the question as 0.015. So this is into 0.015 all raised to 3 by. Okay. So this if you solve it will be 1.71 feet. So this is the this or above. This is the minimum diameter that we need to that the pipe should have. The pipe sewer pipe should have. This is how the design is made. So so if you see commercially the pipe available will be 1.75 feet. We have to round to the upper one. So commercially, the pipes in the market, pipes are available like 1.5 feet, 1.75, 2 feet, that in that way. So we have to take a pipe of that particular value, higher value. That is 1.75 feet diameter pipe we will be choosing to design our design. So this is why we are doing all this. So we started with the intensity. Then we came to the discharge. Then we found the diameter of the pipe. Then we see what all pipes are available. And out of 1.75 feet pipes are available in the market, and then we will be choosing that. Okay, you don't have to, you shouldn't go for a 1.5 feet pipe. You have to go for 1.75 feet pipe. Okay, so you can move to the next question. So the questions coming on now, it will be important. Like uh, first, you understood why we are doing all this. We are trying to design such storm drainages. We are trying to design dams. We are trying to design embankments. We are trying to design culverts. So that is our ultimate purpose. Okay, and the ultimate aim of these courses is also to strengthen your basics, not for exams. If you are going with a profession as a hydrologist, this is all the basics that you need to understand. Okay. So a small watershed of 1.4 kilometer is composed of four different land use types as shown. So there is a watershed, small watershed, it is only 1.4 kilometer square area, and it it has four different land use. Land use, land cover means nothing but build up area, vegetation. If one particular area we consider how much area is build up area, how much area is vegetation, how much area is barren land, right? Like that. How much area we have a very forest cover, dense forest cover. So these are like land use, land cover maps. So these maps we can get. So from that they are saying zero point 0.3 kilometer square area out of the 1.4, 0.3 as a runoff version 0.6. Point 4 has zero point 0.3, 0.5 has zero point 0.2, and zero point 0.2 of the area is runoff version 0.8. So runoff coefficient means it is rainfall by runoff. Runoff by rainfall, right? How much percentage of rainfall is getting converted to runoff? If the runoff coefficient is very high, like if we are taking the case of zero point 0.8, 0.600, it's very high. That is almost the 80% of rainfall is getting converted to runoff. That is very less infiltration is taking place. So if runoff coefficient is very high means it is a urban, it can more like an impermeable or urban area. So maybe this zero point 0.2 kilometer square of that particular watershed is an urban area. That is why we are having very low, very high runoff coefficient. Most of the water is getting converted to runoff. Okay. If the catchment experiences storm of intensity, so it is experiencing a storm of intensity, that intensity I is given for a duration equal to the for a duration equal to the time of concentration. So duration of the storm is equal to the time of concentration. Calculate the peak runoff. So basically, we need to find QP, peak runoff. And with the formula we were dealing with was the rational formula that is given by rational formula is given by C into I into A. So this we can remember, right? QP is a design discharge or peak. Design discharge, we can also call it as peak runoff. That is given by C into I into A. So the problem here is that there are four different C's. There are four different C's given: zero point 0.6, zero point 0.3, zero point 0.2, and zero point 0.8. Which one to fix? So then what we'll be doing a weighted average. Based on area, we'll be doing a weighted average and then coming up the value of C. So C, we can do a weighted average like summation of CIAI divided by summation of AI. So similar question I think I have solved in the class also. That is zero point 0.6 into zero point 0.3, 0.6 into zero point 0.3 plus zero point 0.4 into zero point 0.3 C into area, right? So this zero point 0.3 into area zero point 0.4 plus zero point 0.2 into zero point 0.5 area plus zero point 0.8 into zero point 0.2 area. The denominator will be sum of each of the area. That will be nothing but our total area. Total area is 1.4, I think. Yes, 1.4. So this, if you do the weighted average, you will be getting it as 0.56 by 1.4. That is 0.4. Okay. So we got our weighted average turnoff coefficient. Now everything is given to us. Intensity is given, area is also is not, right? So now we can find QP using the rational formula. So that is QP is equal to, so the units are in mm per hour and intensity is mm per hour and area is in kilometers square, right? So C is nothing but 0.4. Intensity I is given by, it is given the question that is 30 mm per hour. So that is 30 into 10 power minus 3, that will be meter per hour. So this hour, 1 hour will be how much seconds? It will be 60 minutes into 60 seconds. We have to convert. So we want our final answer in meter per second, meter cube per second, right? So we are all substituting everything into meter per meter SI units. So this will be meter, this will be second. We have already done the conversion. In the area, we have to put it in for meter square. It is for 1.4 kilometer square. It will be 1 kilometer 10 power 3 the whole square. That is 10 power 6. So if you solve this, your final answer it will be 4.67 meter cube per second. Okay, so we will be getting our peak discharges 2%. Here, only thing you have to remember, we are doing some unit conversion. So if it is confusing, I can just mention here. So we have C, intensity we are converting. Intensity is how much? It is given as 30 mm per hour. So 30 into 10 power minus 3 meter, right? And hour, 1 hour is 60 minutes into 60 seconds. So this means seconds. So this is what we have substituted here. And also our area is 1.4 kilometers square. That is 1.4 into 1 kilometer is 10 power 3 meter the square. Then you have to square this. That is 1.4 into 10 power 6 meter square. Okay. So this is how we do the unit conversion and we substitute here. Then we will be getting our peak discharge. Okay. So we can move on to the 10th question. Urban catchment has a maximum length of travel. That is, maximum length of travel means the water, the catchment from the farthest point of the catchment water to reach the outlet drainage. That is the maximum length of travel. So that is given as 1,500 meter, and the average slope of the catchment. So average slope to the outlet is 0.1, 0.01. The catchment has an area. Catchment area is also given 2.5 kilometers square. Runoff coefficient is also given. Using Kirpich formula for time concentration and rational method, estimate the peak discharge if the intensity of rainfall is given. So here also we are given with the intensity of rainfall is given, runoff coefficient is given, area is given. We have to find the peak discharge use, but we have to make use of the Kirpich formula also, right? Just a minute. So basically, we have to do two things here. These three are given. You have to find QP. So this we have to find QP. So this you know, if these three are given, we can directly find QP using these three. Okay. So one more thing they are asking using Kirchhoff formula, find TC. So it's something called time of concentration. To find time of concentration of Kirchhoff formula. This is just to introduce to you a formula that is called Kirchhoff formula. Okay, that is being used to find the time of concentration. Time of concentration is nothing but the time taken by the water when it rains, the water from the farthest point, that water to reach the outlet. That is called the time of concentration. Okay, so that we have many empirical equations, but Kirchhoff has given an equation. So that is time of concentration is equal to 0.01947 into L, that is L, that is the length distance from the farthest point. Okay, average distance into slope. Slope is S raised to 0.385. So don't need to by heart all these questions. If at all they are being asked the question, they most probably they would be giving you this formula because it is very hard, difficult to by heart, and these are empirical equations which they are derived for a particular location. Okay, so if it is given in the questions in this way, you should know how to substitute that. Okay, so in Kirchhoff formula, one thing you have to remember is this is L is in meter and slope has no unit, right? So length is given as 1500 meter. So we can substitute that and find TC 0.01947 into 1500 all raised to 0.77 into 0.01 is the slope all raised to minus 0.385. So if we solve this, we will be getting our time of concentration as 34. We will be getting whatever we are getting will be in minutes. That is another thing you have to remember. So if you are dealing with these such empirical equations, unit of the inputs and output we have to be clear. So whatever we substitute in this, we will be getting it in minutes. And we need to substitute this in meters and the slope as known on it. If you substitute the length in meters, whatever the answer we are getting will be in minutes. Okay, so we'll be getting it as 34.5 minutes. So this means if the storm occurs after half an hour, like around after 34 minutes, water from the farthest point will reach the outlet point. Okay, the second part you already know. We are using rational formula. So we have already solved multiple questions using this, using rational formula. So our peak discharge QP is given by C into I into A. So C is given in the question, I is given in the question. We just have to substitute. C is given as 0.4. I is in mm per hour. So I we can substitute as 40 per hour. So 40 per hour we can convert as 10 power 3 meter per hour means 60 into 60 seconds. Okay, and then we have our area. Area is in uh, kilometers square, 2.5 kilometers square. So 2.5 into 10 power 6 meters square. So if you solve this, you will be getting this around 11.11 meter cube per second. Okay, so with this, I will give you, like, if you want to solve this question quickly, questions related to if there is a time constraint, if you want to solve such questions quickly, mostly our intensity will be in the unit of mm per hour. Like in the previous two questions we saw this, it is in mm per hour. And we have our area always in kilometers square. So mostly this will be the unit. So if we want QP in the options, if the QP will be mostly there in meter cube per second. So if this is the case, if these are the case, if these are in this particular unit, instead of you wasting your time in doing this unit conversion, you can remember the formula like our QP as 0.0.27. Just you have to remember this value, this particular value, 0.2778. That's the same CIE. Okay, so if you remember this formula, you you have to substitute now. C has no unit. I should be in mm per hour, and the question it will be in mm per hour mostly, and this should be in kilometers square. So if you substitute this, you will be getting this in meter per second. So basically, 0.2778 is nothing but all these conversion factors. So if I could draw a line like point, for unit conversion, we used all these, right? This we used, and also we used this 10 power 6. So these three, if you solve, it will be coming around 2 points, right? So you don't have to waste your time each time doing this unit conversion and all. If you want, you can remember this value also 2.27. So just multiply it with this and substitute your value of I in mm per hour and K area in kilometers square. Okay, so we can move to the 11th question. So compare the maximum flood discharge QP of a catchment of area is given 100 kilometers square in central India using Dickens formula and in Tamil Nadu using Rice formula. So this is just to give you an introduction of the empirical equation. So we have one equation that is our rational formula, that is QIA, right? So there are multiple equations like empirical equations that have been derived for different location, particularly for India. For central India, based on their like hydrology, their topographical properties, their climatic properties like aridity and all, they have derived simple equations are already derived to find the peak discharge or design discharge. Okay, so it will vary for different locations. For Tamil Nadu region, there we have the Ryan's formula. For central India, we have the Dickens formula, and they have some coefficients like CDCR, coefficient of Dickens, coefficient of Ryan's. These are simple substitution questions, right? So, so to introduce to the to for that we have brought in these questions. First question is regarding the central India that is using Dickens formula. Dickens formula for central India. So for central India, they have derived the formula, and this is given by QP is equal to CD into all the functions of area only. CD equal into area raised to 3 by 4. Okay, so you have to can remember this Dickens formula is CD equation against into area raised to 3 by 4. And we have to substitute this particular area. This area must be substituted in kilometers square. So one thing you have to remember is these are empirical equations and they have units. So area should be in kilometers square. And if you do that, we will be getting our QP in meter cube per second. Okay, so we have QP as CD is 14 into 100 whole raised to 3 by 4. That will be 14 into 31.62. That is 442.68 meter cube per second. Okay, so that is for central India. The peak discharge is coming out to be 42.68. Okay, and second part. So for using the Rice formula, and that is for the Tamil Nadu region. So here QP, the formula is QP is given by CR multiplied by all raised to 2 by 3. Earlier it was 3 by 4, now it is 2 by 3. Okay. So this is the formula, and we can substitute our area is in kilometer square, and this will be getting in meter cube per second. This is how they did the experiments. They took different areas of catchment, and they took for particular area in kilometers where they took the discharge values and they fitted a curve, and then they came up with these empirical equations. Okay, so this is also the substitution. So QP will be CR is 6.8. 6.8 into area is same 100 all raised to 2 by 3. So this will be 6.8 into 21.54, that is 146.47 meter cube per second. The answer will be getting in meter cube per second. So you can remember two formula, Dickens formula for central India, CD A raised to 3 by 4. Okay, and for Ryan's formula for Tamil Nadu region and all, there CR raised to 2 by 3. So just you have to remember A raised to 3 by 4 for Dickens and 2 by 3 for Ryan's formula. Okay, so next we can move on to the next question. So that is also using some empirical equation. So only few numerical equations was taken in the class, so you can remember those. It's not a way, but it is not that complicated ones. So you already learned to A raised to 3 by 4 for Dickens and A raised to 2 by 3 for Rice. Okay. So a highway engineer need to design a culvert for the catchment of area. Area is given in kilometers square. 64 located in the western Ghats of Maharashtra. So in western Ghats of Maharashtra, we are doing this. They are using English formula. So there is something called English formula. Determine the maximum flood distance. So we can look into what is called the English formula. Okay. So here also we have the formula for QP is a function of area only, that is 124 into area divided by root of A plus n.4. So remember this 124A divided by root of A plus 10.4, and A should be in this, A should be, for A should be in kilometer square, and we will be getting QP in meter cube per second, right? So if you substitute, QP will be coming out to be 120.4, 24.64, 24 into 6 4, into 6 4, 64, this area in kilometer square, root of 64 plus 10.4. Direct substitution. Then it will be around 920.12 meter cube per really large value. So this is how we arrived from using the English formula. So these all are like Q as a function of area. Anything you have to remember the formula, you can directly solve this. Okay, so there is one more question using the chemical equations. This is also straightforward. We have already know these questions, these formulas. So this calculate the difference in the peak discharge QP. So area is given. So we need to find the QP. Area is given as 144 kilometers square. If it is located in North Indian plains, so North Indian plains becomes formula CD is given by CD is equal to 6, and for Andhra and Orissa, CD is given for 25. So depending on location, the coefficients for these decay coefficient changes. So North Indian plains, there so basically there's a table. It's a table for each location what this particular CD value have to take. From that we have taken the values in this question. Okay. For Andhra, Orissa and CDs, so how much the difference they are asking. So that is the only thing we have to do is we need to find both uh, both QPs and take the difference, right? Okay. So QP for first case, it will be for, you can start with the North India, North Indian plains, North Indian plains, QP is equal to CD, A raised to 3 by 4, right? 2 by 3 was 4, right? 6 into area is 144, whole raised to 3 by 4. That will be coming around 249.42 meter cube per second. The second for Andhra and Orissa, QP is equal to 25 into 25 is nothing but the CD value for Andhra and Odisha. Area 144, same whole raised to 3 by 4. So this will be around 1039.25. Okay. So the difference. So the difference is in the peak discharge for designing Andhra and Odisha compared to this will be 1039.25 minus 249.42, that is equal to 789.83 meter cube per second. Okay, so if you don't want to waste such time, then we can directly substitute like this. Also, the difference will be directly given by CD1, CD will be higher for Andhra Orissa. CD Andhra Orissa minus CD for North India, the rest will be same, right? Into E raised to 3 by 4. If you do this directly, you will be getting this particular value. You don't need to find for individual cases. Okay, so we have the one more question. Okay, so this will be the closing section. So this is also a bit straightforward. This is also something like how we, if we are given with the rainfall hydrograph. So this is the cumulative rainfall. That this it's called the mass curve. Like rainfall mass curve is given to us. Using this, we have to find the design rainfall depth, identify the maximum rainfall depth, and calculate the corresponding maximum intensity. Okay, so we can do that. So we are given with a proposed drainage system of 2.5 kilometer. So area of the drainage system is given is 2.5 kilometer. Requires to estimate the peak discharge, and the return period is also given of 50 years. The catchment has, so for the 50-year return period, this particular data is given. This particular storm that we selected when given the question has a return period of 50 years. Okay, the catchment of runoff coefficient is given, and at the time of concentration is also given. The following is the cumulative discharge. Identify the max. So they are given time and the cumulative discharge. That is each time how much is increasing. Total like they are getting added up. This is the mass function. Identify the maximum rainfall depth. What is the rainfall depth and the corresponding intensity for 60-minute duration. So here we need to fix for 60-minute duration we have to find. If you see the design hydrograph that is the design mass curve that is given, it is for 30-minute durations. We need to find for the 60-minute duration. For each 60 we have to find. What we are given is for 30-minute duration. So first what we'll be doing, we'll be converting this cumulative rainfall to actual rainfall depth. We have to take differences in each time step. We can get the actual rainfall depth. Once we get the actual rainfall depth, then we have to convert to 60 minutes interval instead of 30 minutes interval. Okay. So we can directly do that in tabular form. So we have our time given in minutes. So it is 0, 30, 60, 90, 120, 150, and 180. And we have our cumulative rainfall depth in mm given as 0, 18, 44, 72, 88, 102, and 110. Right. So this is one project that is given. So now we can find the actual rainfall depth for each that happened during this. So first hour, the rainfall depth is 0. First minute, the rainfall depth is 0. The second minute, the rainfall depth is 18 minus 0, that is 18. Third, first 30 minutes. From 30 to 60 minutes, rainfall depth is 44 minus 18, that is 26. From 90 to 60, it will be 72 minus 44, that is 28. So just we have to take the pairwise differences to get the actual rainfall depth in that particular time. So next to 120, it will be 88 minus 72, that will be 16. Then 102 minus 88, that will be 14. And 110 minus 102, that will be 8. So this is the rainfall depth in mm for each of the interval. So this is for 30 minutes interval. Now we have to take 60 minutes duration depth. So this was for 30 minutes in MM. That is, we'll take 60, 60 together. So the first 0, it is no value. Then 30 minutes we don't have value. But then we will start with our 60 minutes. Okay. So 60 minutes, the total rainfall depth that happened was 18 plus 26. That is, we can add up, it will be 44. Right. And next, in the 90th minute, that is from 30 to 90, that period, how much rainfall has happened? That is 26 plus 28. Right. So these two, from 30 to 60 to 90, so this will be 26 plus 28. That will be equal to 54. Right. Hello? Yeah. So these kind of problems, you don't know, not don't need to write all the steps, right? So what you once I saw, like I mentioned, like you would be sure that the rainfall peak will come in the around in the middle. So initially the rainfall will increase, and in the middle the peak will come, right? So almost either this particular column or this particular column, 90 or 120 it will come. That is sure for you. So you don't have to solve for each of the 10 steps. Okay, then you can directly solve for this. So here you already know 28 by 54. Most probably this will be the answer, 54. So just to check, you can just do for the next time step also. So that will be 28 plus 16. So that is coming around 44. Now we can see it has decreased. So we can stop here. You don't have to do for the next time steps because the maximum depth will be 54. The next time step, if you do also, then also it will be less only. Like the 16.16 plus 14, that is 30. Finally, it is 14 plus 8, that is equal to 22. Okay, so this is our maximum rainfall depth. Now, one more thing, that is intensity. 60-minute duration intensity they are asked. So this also there is no need to make all these tables and all when you are actually solving. Because intensity is nothing but depth by time. So duration is 60. Whatever depth we calculated here, if you divide it by 60, that will be in 60 minutes, that will be converted to intensity, right? So here we are finding it per hour. So 60 minutes means 1 hour. So this will be same only, divided by 1. Actually 60 minutes is 1 hour, right? We are dividing it by 1 hour. This is 44 mm per hour. This will be 54 mm per hour, 44, 30, and 22. Basically, we are divided the previous value by 1 hour. Okay. So here also the maximum intensity we are getting it as 54 mm per hour. So finally, we'll be concluding our answer as so our maximum depth is so maximum depth we are getting as P is equal to P60 is equal to 54 mm, and intensity of 60 duration is equal to 54 mm per hour. Okay. So that is how we solve the first part of the question. So this would be, and there is one more part for this question. It's very simple. You just apply the transfer formula here. So this is just to show you how we came up with the. So we were given with us a particular return period rainfall data. Right, the storm cumulative value was for 50 years return period. So from that, we found the maximum peak rainfall depth for 60-minute duration. So duration of storm. So here the duration of storm we are fixing at 60 because so here the time of conservation is 60, right? So usually when we design storm drainages, the time of conservation, that is the maximum time taken from water from the farthest point to reach the outlet, that we will be taking as our uh, duration of the storm. The storm duration, design storm duration. Like rainfall can occur for 1 hour, rainfall can occur for 2 hours, 3 hours, 5 hours continuously. So here we fix our design storm as 1 hour because 60 minutes because our time of concentration of the gas well was 60 minutes. So that is the assumption that usually we will do. Okay. So first we got the design storm intensity with us. Now we have to find the design flood or design discharge. So from the storm intensity question, a regional IDF curve was developed. So using the IDF curve, yeah, I asked for it. So one way is to we from the data that is given with the particular return period, we came up with the design intensity. Another way is that similar to the previous some questions we did before, they will be doing multiple targeting data from the stations and they will develop a empirical equation for the IDF curve. So IDF curve, I think it is clear to you. IDF is nothing but intensity, duration, frequency curve. So it is intensity, duration, frequency. So this curve will be having it will be intensity versus duration plots and for different return period. Return periods given by frequency. And these equations they will be modeling and empirical equations will be given. So therefore the question in that particular region, this is the design intensity. Okay. So here T is return period, 1 by T is the frequency then, D is the duration. So earlier we fix our duration as the time of concentration. So now also we can fix it as time of concentration that is equal to 60 minutes, right? And it should be D in the empirical equation should be in hours. So that will be equal to 1 hour. And return period is given the question as 50. So 50 years, right? So we just have to substitute this in this particular formula, then we will get the design intensity. So find the design rainfall intensity at the first part. It is 7.2 into T is in years. It is 50 raised to 0.22 divided by D in hour 1 plus 0.4 all raised to 0.75. So we will be getting our intensity in the unit centimeter per hour. So that will be equal to uh, somewhat 17.02. You can solve this and try 1.285. This will be coming around 13.245 centimeter per hour. Okay. So whatever if you substitute the empirical equation, whatever units we substitute, prescribed unit we substitute, we will be getting our unit in that. And now we can, so this is in centimeter per hour. So now we can find the second part of the question is to find the peak distribution rational formula. So this is almost very clear to you now, right? CIU. So C is given, runoff coefficient is 0.35 and I is, we can do one thing, we can substitute, we can use a shortcut form like that. I we can substitute in mm per hour. Usually it will come in mm per hour. 13.245 centimeter, we can write it as 132 into 10, right? 132.45 mm per hour. Into area, we can put in kilometers square. So area of the catchment was mentioned in the question as uh, 2.5 kilometers square. So we don't have to do any unit conversion here. This is kilometer square. If you don't need to do any unit conversion, you just have to multiply this with the factor that I just explained you before, 0.277 meter. We will be getting our answer in meter cube per second. So if you solve this, this will be coming around 32.19 meter cube per second. So this is using the IDF curve. So this is what we did here was we for a particular duration we found out our maximum intensity for 50-year return period. Like so similarly, we can do for different durations. So here we for 60-minute duration we got our peak flood as this much. Peak intensity is 54. Now for 90-minute we can do we will get for 90-minute duration the peak intensity will be getting. For 100 years, 100 minutes duration, we can get another value. So these values for 50-year return we will be getting. Now for another return period, we can get a rainfall data and do the same for this. Then we will be deriving an IDF curve. So that is a bit complicated task that has to be done with multiple trials. So that's why I directly gave you a equation that is has been derived by the hydrologist in that particular catchment. So using this intensity equation, so these are the trials that we do to derive this equation. Okay, once we derive this equation for our catchment, then we will be substituting these values and getting the design intensity. Once we have the design intensity, we can put in the rational formula to get the final peak distance. Okay, so with this, I will close the section. So this was the last class, and as you said, if you have any doubt, you can put a mail. So first, I will get prepared with whatever doubt you are having. So those portions I will get prepared and check with you your time, and then I can come in online to I'll keep a Google Meet meeting, and we can solve those questions. So this will be my last class, and if you have any doubt, you can contact me. My name is Akhil, and my email ID is gmail.com. So thanks for joining this section. So you can contact me through my mail for further doubts. Okay, I'm closing.